by conservative forces? Of course, in order to answer this question, we have to define what a conservative force is. So before we answer this question, let's look back at our work energy theorem. We discussed how the total amount of work done by all of the forces, all added up, they're scalar quantities, you just add them up, no direction, no head to tail, no Pythag or anything like that. Add up all the work, that's equal to the change in the kinetic energy. Another way of writing that is the total work equals KEF minus KEI. Another way of writing that is add the initial kinetic energy over to the other side, and you have the initial kinetic energy plus the total work equals the final kinetic energy. You could use this formula to solve all of the work energy problems that we do. However, there's an easier way, and that's what this lesson is all about. So this here I'm going to call the original work energy formula. And what we're going to build is the new and improved work energy formula. Now some traditionalists would be like, you know, we don't need no improved work energy. No, we need an education. Okay. We don't need a improved work energy theory. This here covers it all. You know, just calculate the total amount of work, add it to the initial kinetic energy. That'll tell you the final kinetic energy. However, there is an easier way. So in order to do this easier way, we're going to rewrite this equation, but we're going to break the total work up into two categories. One is the work done by all the conservative forces, referred to as conservative work. Two, the work done by all the non-conservative forces, referred to as non-conservative work. And of course, this still gives you the final kinetic energy.
Can we call the non-conservative forces liberal?
No. I must say, because this came up in my afternoon class yesterday, that in over 20 years of teaching this topic with conservative work, non-conservative work, no joke, it's never come up in class as a discussion about the political nature of this. Yeah, and it's just interesting how this year politics is so much on the forefront of everyone's mind. It's very polarizing, whether you're conservative.
You should say which year it is.
Yeah, it's 2016.
It's 2016.
It's 2016, ladies and gentlemen.
President-elect Donald Trump.
President-elect Donald Trump.
It's a bad year.
It's a great year.
As you can see, very opinionated. Now, where we're headed, instead of calculating all of the works done, in the future, we're not going to calculate the work done by conservative forces. The work done by conservative forces is going to be calculated an easier way by using potential energy terms. So we're going to swap out work done by conservative forces, and we're going to replace that And many times it's way easier to calculate these potential energy terms than it is to calculate the work done by the conservative forces. So that's where we're headed. But what we need to do now is just define what conservative work is. Conservative work is independent of the path taken between the start point and the end point. No matter which way you travel between the start point and the end point, the work done by that particular force will give you the same value. So conservative work does not depend on the path taken. Yes?
Why are they called conservative words? Like, where does that come? Like, what do they? Why?
What we're going to see is when we only have conservative forces, this quantity, which we're going to introduce soon, called mechanical energy, is conserved. When we have non-conservative work, then this quantity, again, that we're going to introduce soon, mechanical energy, is not conserved. So that's a great question, and hopefully by the time we get through here, you'll have a better sense of that. So an example of a conservative force is the force due to gravity. So an example of conservative work is the work done by the force due to gravity. Now, I'm not going to actually prove all paths, but what I am going to do is prove how, if we go back and look at the example we did the other day, and we did the work done by the force due to gravity, and we got negative 300 joules, we figured that out by saying the object went straight up the ramp. Well, after our little break, what we're going to do is we're going to calculate the work done by the force due to gravity if we took a different path to the top. What if we slid the box straight across the bottom of the ramp and then straight up vertically to the top? When we calculate the total work done by the work due to gravity, by the force due to gravity, and we take this new path over and up to the top, guess what the work done by the force due to gravity is still going to come out to be? Negative 300 joules. So take a break, come on back.